For billions of years, stars shine as bright beacons across the universe, fueled by internal nuclear fusion reactions in their cores. Yet when a wandering star strays too close to a supermassive black hole, its cosmic life is terminated in a violent and breathtaking cataclysm. Astrophysicists call this violent event a tidal disruption event, or TDE, where extreme gravitational shear forces overpower the star's self-gravity. Differential gravity pulls the star apart in a brutal process astrophysicists call spaghettification, stretching stellar plasma into long, glowing ribbons. Half of the star's shredded gas is flung out into interstellar space, while the remaining half spirals into the black hole at relativistic speeds. This sudden feeding frenzy ignites luminous flares of ultraviolet and X-ray radiation that outshine entire galaxies for months. Welcome to how black holes destroy stars, step by step. Step 1, the fatal orbital approach and the Roche limit boundary. A star orbits peacefully near the dense core of a galaxy, surrounded by millions of neighboring stars in a dense stellar cluster. Gravitational nudges from nearby stars alter its trajectory, sending the star on a headlong plunge toward the central supermassive black hole. As the star approaches, it crosses an invisible mathematical threshold known as the tidal radius, or Roche limit. The Roche limit defines the precise distance where the black hole's external tidal gravity exceeds the star's internal self-gravity. Because gravitational attraction falls off with the square of distance, the near side of the star experiences a vastly stronger pull than the far side. This immense gravitational shear forces the spherical star to distort into an elongated ellipsoid shape. Stellar gas on the near side is accelerated forward, while gas on the far side is pulled back relative to the star's center of mass. The star's internal hydrostatic equilibrium breaks down completely, causing internal pressure forces to fail. Step 1 Summary: Crossing the Roche limit marks the point of no return where tidal gravity overcomes stellar self-binding. Step 2, Tidal gravitational shear and spaghettification. Once past the tidal radius, extreme differential gravity squeezes the star sideways while stretching it along its direction of motion. Astrophysicists call this extreme gravitational distortion spaghettification. The star is squeezed into a thin, elongated ribbon of superheated hydrogen and helium plasma millions of kilometers long. Nuclear fusion in the core ceases instantly as internal pressure and density profiles are violently disrupted. Tidal forces overcome the electrostatic bonds holding atoms together, creating a stream of ionized stellar plasma. Hydrodynamical supercomputer simulations show the star stretching like a ribbon of taffy pulled from both ends. Temperatures within the stretched stellar gas rise to millions of degrees Celsius due to intense tidal compression. The star's identity as a bound astronomical object is destroyed forever. Step 2 Summary: Spaghettification shreds the star into a thin, relativistic plasma stream. Step 3 Stream elongation and mass bisection. As the shredded star passes pericenter, its closest approach to the black hole, the stream splits into two distinct components. Roughly 50% of the stellar mass gains unbound parabolic orbits, receiving a gravitational slingshot boost. This unbound gas stream is ejected out into interstellar space at thousands of kilometers per second, enriching the galaxy with gas. The remaining 50% of the mass remains gravitationally bound on tight elliptical orbits, destined to return toward the black hole. The bound gas stream arcs around the black hole in a long, curving trajectory. As the returning stream loops back toward the center, it collides with itself in a process called stream-stream intersection. Self-intersecting gas streams create violent hydrodynamical shock waves, converting kinetic orbital energy into intense thermal heat. These shock waves decelerate the gas, allowing it to settle into orbit around the central mass. Step 3 Summary: The star's mass is split, half is ejected while half returns to form a new structure. Step 4 Circularization shocks and accretion disk formation. As the returning gas shocks and loses orbital energy, it undergoes circularization. The elongated gas streams wrap around the event horizon, forming a glowing, superheated accretion disk. Friction between gas layers moving at different orbital speeds heats the accretion disk to hundreds of thousands of degrees. Magnetic fields thread through the swirling plasma, driving magnetorotational instability and creating powerful viscous drag. This drag forces gas to lose angular momentum and funnel inward toward the event horizon. The accretion disk glows with extraordinary brilliance, outshining every star in the host galaxy combined. Matter orbiting near the innermost stable circular orbit moves at over 50% the speed of light. The black hole transforms from a quiet dormant monster into a temporary hyperluminous beacon. Step 4 Summary: Circularization converts shredded gas into a brilliant, superheated accretion disk. Step 5: Relativistic jet launching and magnetic acceleration. If the central black hole is spinning rapidly, magnetic fields trapped in the accretion disk are twisted into tight helical funnels. The spinning event horizon acts as a giant dynamo, launching powerful twin relativistic jets from its polar regions. These plasma jets blast out perpendicular to the accretion disk at over 99% the speed of light. Relativistic jets punch through surrounding interstellar gas, producing intense non-thermal gamma-ray and radio emission. NASA's Swift and Fermi space telescopes have detected jetted TDE flares spanning billions of light-years across space. Particle acceleration within the jet accelerates protons and electrons to extreme relativistic energies. Step 5 Summary: Spinning black holes launch twin relativistic plasma jets into deep space during stellar consumption. Step 6 Luminous UV and X-ray flares observed by space telescopes. As the accretion disk peaks in density, it releases a massive bright flare of optical, ultraviolet, and soft X-ray radiation. Astronomers on Earth detect these flares using wide-field sky surveys like the Zwicky Transient Facility and OSIS-SN. NASA's Chandra X-ray Observatory and Hubble Space Telescope track the thermal evolution of the flare over months and years. By analyzing the flare's light curve, astrophysicists can measure the mass of the destroyed star and the black hole's spin rate. Spectroscopic observations reveal strong emission lines of hydrogen, helium, and nitrogen from the shredded stellar interior. Famous TDE events like at 2019 KIS have provided unprecedented real-time movies of stars being swallowed. These observations allow scientists to study dormant black holes in distant galaxies that are otherwise completely invisible. Step 6 Summary: Bright UV and X-ray flares reveal hidden black holes shredding stars across the universe. Step 7 Final consumption and gravitational decay. Over months to years, the rate of gas falling into the event horizon steadily declines following a characteristic power law decay curve. The accretion disk cools, dims, and eventually dissipates as the last remaining stellar gas crosses the event horizon. The black hole returns to its quiet, dormant state, having gained a fraction of solar mass from the destroyed star. Tidal disruption events occur roughly once every 10,000 to 100,000 years in an average galaxy. Next-generation observatories like the Vera C. Rubin Observatory will discover thousands of TDE flares every year. Studying stellar destruction helps scientists map supermassive black hole populations across cosmic time. Human technology transforms distant cosmic cataclysms into profound insights about gravity, light, and spacetime. Supermassive black holes act as cosmic regulators, releasing feedback energy that shapes host galaxy evolution. The stellar material ejected into interstellar space will eventually cool and condense into new generations of stars and planetary systems. This cosmic recycling process connects the destruction of ancient stars to the birth of future solar systems. The universe remains a dynamic arena governed by extreme physics, eternal cycles, and extraordinary beauty. Every tidal disruption event observed by astronomers reveals crucial clues about the growth history of black holes. From supermassive singularities in galactic cores to intermediate mass black holes, stellar destruction probes extreme gravity. Relativistic plasma jets launched during TDEs accelerate cosmic rays to near light speed across intergalactic space. Orbital space telescopes like NASA's James Webb Space Telescope continue to study gas dynamics around galactic centers. Ground-based radio arrays track expanding synchrotron emission from TDE blast waves for years post-disruption. These multi-messenger astronomical observations validate Einstein's equations of general relativity under maximum gravitational stress. As observational instruments become more sensitive, astrophysicists will capture TDE flares from the early universe. Understanding how black holes devour stars allows humanity to unravel the birth and growth of galaxies. Our own Milky Way's central black hole, Sagittarius A*, shows evidence of past stellar disruption flares millions of years ago. Thank you for joining us on this exploration of how black holes destroy stars, step by step. Keep looking up at the night sky, and never stop wondering about the ultimate mysteries of the cosmos. Farewell, and see you on our next deep space journey.